This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. We have been hearing it for years. Climate change is happening. What I'm about to present to you is fact. These are reliable measurements with multiple peer-reviewed papers confirming the information. Atmospheric carbon dioxide levels are the highest they've been in over 400,000 years, confirmed by our analysis of hundreds of samples of Arctic ice cores, tree cores, and isotope ratios in fossils. Average global temperatures have risen by 0.8 degrees Celsius since the Industrial Revolution began, with two-thirds of that change occurring since 1975. The evidence is overwhelming. This is fact. You are wrong if you deny it. If these trends continue, and I really shouldn't say if because they will continue, we are going to continue seeing stronger storms, more heat waves and droughts. Sea levels will continue to rise even after the ice caps have vanished in the summer months in about 30 years. And to really make you motivated to care about this, the world's economy will suffer. We have been making strides in the technology required to reduce our emissions of carbon dioxide, but the changeover is happening too slowly. The most effective thing our world has done in the past 10 years in battling carbon emissions was going through a global financial crisis. Countries like my own are continually missing carbon targets. We're going to face up to €600 million in fines every year after 2020 until we fulfill our promise of reducing our carbon emissions by 20%. That money is going to come out of our pockets through carbon taxes. Maybe then we will start to take climate change seriously. We aren't making significant decreases in carbon dioxide emissions. We've only really leveled out, which is not good enough. So if we aren't making a difference by reducing emissions, maybe we can reverse climate change. Maybe we can engineer our climate. And there has been multiple suggested methods of doing that. In this new video series, we're going to explain how several geoengineering methods intend to work and their potential impact on the world's climate. The first plan we will examine is afforestation. Afforestation is pretty self-explanatory. Plant trees, allow them to grow, and store carbon in their wood. The problem we run into is finding large enough spaces to plant forests that would have a significant impact on the climate and that would not negatively affect the economies of the countries employing the method. Taking land that could be used for agriculture just isn't a realistic solution. No one is going to agree to it. Our options are limited, but we happen to have huge expanses of land on Earth that are not being used for anything productive. Deserts. Now I know what you're thinking. Deserts are not the best place for growing anything, but with water desalination technology rapidly advancing, this isn't as far-fetched as it may seem. We are going to examine the feasibility and effect of afforestation in the two largest subtropical deserts in the world, the Sahara and the Australian outback. These are the perfect candidates for afforestation. Neither have large competing human populations, agricultural activity, or large natural animal and plant populations. Conveniently, they are also in the subtropical zones where a 12-month growth cycle is possible, maximizing our carbon capture potential. To maximize our potential further, we need to pick a suitable tree. The tree we choose will need to be suited to this climate, be evergreen, grow rapidly, and be useful as a commercial resource. The Australian Eucalyptus grandis will be the candidate for this study, which also comes with the added benefit of being a habitat for these cute little shits. Before even bothering to worry about how this would be done, let's first see if it's worth being done. Let's first look at the Sahara as an example. Ultimately, we are trying to sequester atmospheric carbon dioxide by storing it in wood. Every 10,000 square meters could hold about 1,000 trees, and taking this patch of the Sahara between the 16 degree and 50 degree longitudes, we have about 9,800 billion square meters of land. Ignoring land needed for infrastructure, that's about 980 billion trees. Planting a forest of this size would increase the world population of trees by 33%. That's a lot of trees. Estimates show that this would capture between 6 and 12 gigatons of carbon per year for about a century, before it would meet a steady state where growth would slow and carbon dioxide in would equal carbon dioxide out. 6 to 12 gigatons would capture between 16.3% and 32.6% of our emissions per year, with humans generating a total of 36.8 gigatons of carbon dioxide in 2017. Ideally, we wouldn't just let the trees grow and forget about them. We would systematically cut them down and use them for construction, synthetic feedstock, or convert them to liquid biomass fuel to replace our dwindling fossil fuel supplies and burn that fuel in a power plant with its own carbon capture technology, which would reduce emissions further and produce new economies for these desert regions. Australia's desert is about 60% the size of the Sahara, and so we could add an additional 60% to that figure to bring our best case scenario to just over 50% capture of our emissions per year. bringing our emission levels per year down to levels equivalent to that of the 70s. On the surface, this seems great, but what effect would this actually have on our environment? There are multiple things we need to consider. First of all is the irrigation itself. A managed forest of this nature would need 500 millimeters per year of water, which equates to 4,900 billion meters cubed of water per year for this number of trees. Where is all this water going to come from, and at what cost? Freshwater supplies are obviously rare in the Sahara, but surprisingly not as rare as the Australian outback. The world's largest groundwater aquifer actually resides beneath the Sahara and is shared by 4 countries: Egypt, Libya, Sudan and Chad. And it is not alone. New studies show the Sahara is sitting on vast reservoirs of groundwater. This groundwater supply is vital for many African countries, with it often being the primary source of fresh water for their populations. Draining at an industrial scale like this comes with ethical concerns, as it is a non-renewable resource. Even these vast reservoirs of water would run dry within a few years when pumped on this scale. However, the cost of desalination of seawater has dropped dramatically in recent years, thanks in large part to countries like Israel, the United Arab Emirates and Saudi Arabia, who have invested in the technology and all get over 50% of their drinking water from desalination plants. This technology still requires energy, and energy comes with a cost, both monetarily and as a source of carbon dioxide. It requires approximately 1.5 kilowatt hours of energy to desalinate a meter cubed of water. We then need to pump the water to a height for distribution. With the average elevation of the Sahara at 450 meters, this would require a further 2.5 kilowatt hours per meter cubed, bringing our total energy consumption to 4 kilowatt hours per meter cubed of water supplied. The cost of this in terms of carbon footprint and actual cost will vary with the energy source used, but considering the location and nature of the project, a mix of solar power and biomass energy with carbon capture technology attached to its exhaust should be used. Let's focus on a purely solar powered process for now, as biomass is more expensive and has a larger carbon footprint without carbon capture technology, though it would become cheaper as the project matures thanks to the cheap source of fuel on its doorstep. Solar energy costs about 10 cents per kilowatt hour with a median carbon footprint of 72 grams per kilowatt hour. Putting all this together, the total energy needed to irrigate this forest with 4,900 billion meters cubed of water will be 19,600 terawatt hours a year, at a cost of $1.96 billion a year and a carbon footprint of 1.4 gigatons of carbon a year. Ignoring infrastructure costs, which would likely push the initial cost into the trillions, this puts our total carbon capture for the Sahara at a best case scenario of 10.6 gigatons a year at a cost of $184 per tonne of carbon dioxide captured. Expecting poor African nations to fund this alone is unrealistic, so it would be reasonable to expect countries to pay for this project through carbon taxes, like those that will be placed on Ireland in 2020, and thus allowing them to offset their own carbon emissions with funding to the project. A litre of petrol, when burned, emits approximately 2.6 kilograms of carbon dioxide. Thus, placing a carbon tax of about 48 cents per litre of petrol could pay for the project, if we sell 4 billion litres of petrol with the added carbon tax, which is about the total petrol and diesel consumption of a small country like Ireland. So it's possible at a high cost, but if the project can stop climate change, maybe it's worth it. That's the next problem we need to address. What effect will the forest actually have on the world's environment? With the help of climate models, we can start to get a clearer picture of what all this money and effort would give us. Temperature being the top of our list of concerns. Local temperatures would be affected most due to the evaporative cooling caused by the increase in soil moisture. This would seed clouds and increase local precipitation substantially, allowing us to reduce our ongoing costs, with heavier irrigation only needed in drier months from May to October. Local evaporative cooling does not decrease overall global temperatures, as it just transports the heat within the Earth's atmosphere. Critically, we want to reduce the amount of heat retained in the Earth's atmosphere by reducing greenhouse gases, allowing heat to escape the system entirely. One of the biggest concerns with a project like this is the modification of Earth's albedo. Albedo is a measure of how reflective a planet is. A higher albedo, it means we reflect more sunlight back into space rather than absorbing the solar radiation, and thus increasing the temperature. Forests have a very low albedo. They are literally designed to absorb solar radiation, whereas snow and ice have a very high albedo. They reflect quite a lot of light, as does sand. Placing forests over regions where sand once resided will reduce the world's albedo. Alone, it will actually negate the heat lost through reduction in greenhouse gases. In this climate model, however, the clouds seeded from the forests help to counteract that decrease in albedo. The study shows an overall decrease in surface temperatures, but a significant increase in ocean temperatures surrounding the forests. The conclusion of the primary paper used for research in this video is fairly ambiguous, with no definitive answer to whether the project would have a net negative or net positive effect on global temperatures. While other papers that did not factor in the increase in cloud cover affecting albedo, suggesting that afforestation in the Sahara and Australian outback would increase global temperatures by 0.12 degrees Celsius by 2100, compared to a control model where no afforestation occurred. We also need to worry about the decrease in fertilization that would occur due to Sahara dust no longer being transported to the Amazon and the Atlantic Ocean, which would likely decrease plant and plankton growth and thus negate much of the carbon sequestration that this forest would provide. The desalination plants would also need to carefully manage their output of highly concentrated salt water, as dumping undiluted salt water into the ocean would wreak havoc on the local aquatic environment. Overall, I think the idea is an interesting thought experiment, but practically shows little evidence of benefit for the labour and cost needed, and could potentially open a Pandora's box of unforeseen consequences. Ultimately, our best tool for combating climate change will be to decrease our carbon emissions, and that solution is staring us right in the face through cheap solar and wind energy. We need more people acting on this. We need more people funding and researching alternative energy sources. You can become one of those people today by taking this course on solar energy on Brilliant. In this course, you will discover the principal methods of harvesting energy from sunlight, from both concentrated solar power and photovoltaic cells, starting from the fundamental physics principles. By the end of the course, you will be able to answer practical engineering questions and have a better understanding of the considerations in servicing utility-scale electric grids. The best way to understand is by applying concepts yourself, which is exactly what Brilliant allows you to achieve. This may initially sound complicated and scary, but Brilliant guides you through problems that are broken into digestible sections that bring you from knowing nothing to having a deep understanding of the physics and math that underlie our lives. Feeling inspired? Then go to brilliant.org/real-engineering and sign up for free. And the first 73 people that go to that link will get 20% off their annual premium subscription. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit, and Discord server are below.